My name is Victor Frost. So I've been at the University of Kansas since the early 1980s, and I've been teaching the fundamentals of communication systems off and on since I joined the faculty. And what I'm going to talk about today is what I've done over the last couple of years in transitioning this course to being taught using a Wolfram notebook that covers all the topics that we deal with in this class. So there's the abstract that you can pull down with the presentation material. So kind of an outline, give you the philosophy, the motivation and the philosophy of the course, some of the issues we've run into over the years in teaching this particular course, the solution, talk a little bit about the benefits for the instructor, talk about how you can get the book, then show some examples of the interactivity and some inline questions that I had, and then wrap it up. So the motivation is to bring the fundamentals of communication systems alive using interactive graphics and dynamic performance metrics calculations in inline questions. Another purpose is to, as soon as possible in the course, introduce the students to concepts of communication systems that they can relate to engage them into things that they use every day. And you'll see as I go along how we've done that. The philosophy behind this was to keep it simple. I wanted to have the whole tech ebook in one file. Recently, there's been another nice book in related topic, the Fourier transform using Mathematica that Joseph Goodman from Stanford has posted. And I think that's effective for the students. It's easy for them to use. Another background I wanted to do is I wanted this to be a open educational resource material. I think that's a trend that's happening. You can go to that link and you can find quite a few open textbooks that are there. These are free access, openly licensed information that support research and teaching. At KU, our timetable lists kind of indicators of the cost for the materials for each class, and students are very sensitive to that. And some of the textbooks in this area have really gotten expensive, and this is a way to benefit the students. It's free to the students. Being open educational resources, KU has what's called KU ScholarWorks. So the resources posted on KU ScholarWorks, so it's not on my personal webpage. So if I disappear, it doesn't disappear. It's there and archived. It's got an ISBN number and everything. So I can just point the students to the KU ScholarWorks to get the book. And so the student version only requires the Wolfram player, so they have no cost. And that was one of the philosophies behind developing the material. The other issue is to keep the technology relevant. Like I said, I've been teaching this course since the early 80s. And back then, one of the key examples that we went through was analog color television and how that worked. Well, that's legacy and doesn't even exist anymore. So for several years when I've been teaching this, that doesn't relate to the students at all. So you had to have something that was more relevant to their current experiences. Also, some of the communication theory, the mathematics, kind of hides the concepts and the trade-offs, and it was important to try to bring those to the forefront to help the students. Also in comm systems, you have to view the system components both in the time and frequency domain and see what's going on and visualize in your head both of those. And so interactive graphics really helps doing that. Also, there's complex trade-offs, system trade-offs between bandwidth, modulation, receiver complexity, transmitter power, antenna size, what carrier frequency you're on, your propagation environment, and distance. And one of the goals was to try to get the students to understand these trade-offs by the end of the semester, and seeing them visually, I think, helped. So overall, is try to apply the understanding of the fundamental concepts without them getting lost in the mathematics of the material. So the solution here was to reorganize the material a little bit, and I'll mention that. The other thing is to show a lot of these properties using Wolfram interactive graphics. Kind of as background, over the years, ever since I found I've known about Mathematica for a long time, but when I really became familiar with using the manipulate function, I use that in several of my classes. And so I had kind of a repertoire of interactive graphics already built up. And also the Wolfram demo was a good resource. I was able to use some of those, reuse some of those without having to develop them on my own. And this enabled me to show some interactive, use these to show system trade-offs. In COM systems, it's common to use link budgets to trade off one parameter for another, and that was also helpful. One other thing that this enabled me to put in here was I have probably 100 plus, maybe more interactive inline questions that the students can answer as they go along, and it just tells them whether they're right or wrong. These aren't graded. There's no auto grading or anything involved. It's just kind of a way that they can confirm that they understand some of the concepts. Also, when I lecture, I can work those inline questions as I go along. That helps illustrate the concepts. Here's the table of contents, which obviously I'm not going to go through in detail here. The main thing is that I start out by talking about bits, because the world, starts out in bits a lot, email messages, text messages and such. Then go on to doing double-sideband suppressed carrier. And that's really the only math that you need to do advanced modulations, even though they say they're phase modulation, like binary phase shift keying, quadrature phase shift keying, quadrature amplitude modulation. Theoretically, all you need to understand is double-sideband suppressed carrier to do that. So I was able to put that very early in the semester and then introduce OFDM, because OFDM is what's used in 4G, 5G, Wi-Fi systems. And so it would relate directly to what they already have. So I was able to push this material earlier in the semester, which is kind of unique in communication books. Most of them typically talk about commercial AM and then commercial FM, and then they get to digital comm later. So I pushed that material forward. Now, the benefits for the instructor is that I taught from this material last spring, and I taught directly from the notebook using the classic slideshow palette. It worked pretty well. The graphics were all there. These interactive questions were all there. And it just helped doing that. I could engage the students with the system trade-off studies kind of in real time as I'm doing the lectures. For example, when I was teaching the class last spring, the Perseverance Mars rover had just landed, and I pulled out some of the parameters of the communication systems for that and was able to use that as an example in class as I went along, and to show some of the trade-offs that would be involved. And then I wrote all of the homework problems as separate Wolfram notebooks. The end of chapter problems don't have in what I give the students, obviously don't have the solutions. But if anyone would be interested in getting the solutions to the homework as Wolfram notebooks, I'll provide those. And then if you need to, obviously it's easier for me when I teach it again to go change numbers, and it would be for anyone else to come up with new homework problems just directly from those notebooks. Just as a side note, in other classes I'm teaching, I'm finding I'm developing my tests and other homework problems as Wolfram notebooks, because it's easier to go back and change them and make sure I don't have errors. However, you have to tell the Wolfram notebook the right numbers or you still get an error, which I did on a test I just gave back a week or so ago, but it does help things to do that. And so all the homework problems at the end of the chapter are in notebooks. So here's the information about the book itself. It's the ISBN number. It's in the KU libraries. And here's a link to it. If at the end we have time, I'll maybe go show you what the link looks like on the KU Scholars page. Anyway, that's the information about it. So I want to spend the next 10 minutes or so showing some of the interactive graphics and how I bring them into the classroom. So this is one I use at the very introduction lecture, where I show them what the problems are in the communication systems. So I can make the noise very small and the bandwidth large. And so what we say in an ideal system, all you'd have to do is delay and scale the system. So if you didn't have noise or multipath in the channel, then you could detect the received pulse or the received signal almost ideally. Here's the transmitted pulse and here's the received one. And so then I can tell them, okay, in this class, we're going to deal with what happens when you have noise and you have fading in the channels, so the pulse is distorted. And now it's going to delay, and you're going to have to say, is there a pulse present and where is it? And I think that brings to light kind of the whole problem we're dealing with in the semester about what kind of modulation schemes we need to deal with, and fundamentally, how do you pull the signal out from the noise. And I'm a visual learner, and I hope that the students at this point will see, oh, that's what we're going to figure out as the semester goes along. Another aspect of comm systems that you have to deal with is showing systems in the time and the frequency domain. So here's a pulse, just showing a Gaussian pulse in time, and this is showing the Gaussian pulse in frequency. And I have this set up where it automatically calculates the RMS bandwidth as you change the parameter. So when I introduce the concept of the bandwidth, they see the parameter changing as you go along. When you teach sampling, the sampling theorem, the Nyquist sampling theorem says that if you sample at twice the highest frequency present, you can recover the signal. Well, with real signals, you have an impairment because the orange here is the original signal, and the blue is the sampled spectrum. So this is a way of telling the students, well, even though you're sampling, the original spectrum is not band limited. So you're always going to have some practical error between the sampled spectrum when you filter it and the original spectrum. And how, as you sample faster, that rate goes, that error is reduced. In the trade-off, again, you're trying to show trade-offs. Oh, if I sample faster, my sampled spectrum is closer to my original spectrum, but I have to pay for that in additional samples per second or bits per second. And so having an interactive graph that shows the sampled spectrum as you change the sample rate directly illustrates that concept. Another important concept that's always difficult for the students to understand is intersymbol interference. And that happens when you don't have the right pulse shapes. An ideal particular pulse shape that we talk about a lot is called a raised cosine pulse. And the property of the raised cosine pulse is that the zero crossings happen at integer numbers of time. And the ideal, or the one that we start with a discussion, is a sync pulse that looks like this, that has this spectrum. But the trade-off here is that if you increase what's called the roll-off factor, you trade off more bandwidth, but you're not as, and I illustrate this, I'll show you on another slide. You maintain your zero crossing properties, but you're going to be less sensitive to system impairments, but you're using more bandwidth. And so this interactive chart shows that directly. This is again showing what happens with intersymbol interference. And to explain this, the blue line are the exact samples that you're trying to recover. The receiver output is this red line. And as you change the system parameters, you're seeing how sensitive, if you have the system parameter set just right, what you show the students is if you sample the red, you get the signal pulses that you want out, the values that you want. And as you change the roll-off factor, you still get those. But what this plot really helps to show is that if there's an impairment, then using a large roll-off factor, which you're paying for with bandwidth, your error in making that sample is less. So what I'm doing by changing this bandwidth parameter is basically saying what happens if my system's not perfect. But if I use a roll-off factor of 1, then my sample values at the sampling time are still pretty good. And I think the students understood what was happening by seeing this interactive graphic this way. A standard way of showing intersymbol interference is an eye diagram. And so this shows an eye diagram, and you can add, this runs fast. You see each set of signals. This is like overlaying a, syncing up your oscilloscope to the pulses that are coming in. And back in the day, I used to have a set of view graphs that I overlaid on a projector to show this. But this allows me to actually change the system parameters and show how it changes the eye diagram interactively. One of the things we also do is show approximations. So this shows what's a large signal approximation that we need to use for analyzing noise in FM systems. So it's saying, here's the in phase and here's the quadrature, and how we can make that approximation. This is showing the students a way of showing the exact solution versus the approximate solution when you're dealing with the noise performance of FM. And what happens in FM is you have a threshold effect that below the threshold, this is the input signal to noise ratio, and this is the output. Below the threshold, your performance degrades rapidly. Above the threshold, our approximation works. And the point where that approximation is valid changes with our modulation index. So it was always hard to get that concept across without this type of interactive slide. Another one is the, this is 8 BPSK in noise. If you have no noise, then the in phase and quadrature points are in a circle. And you can change the amplitude, and that pushes them further apart. These lines here represent the noise threshold. And what this allows the students to see is if you have noise, you can actually start seeing the errors that happen. Like here, this symbol was an error. So these 3 bits are an error. And as you make the noise larger, you get more error. And the way to compensate for that is I can transmit more power that pushes these signals further apart. I have an antenna pattern. I'm running out of time. I'll skip that one. This is a link budget that you can put in all the parameters in a standard link budget. This is a way of doing the link budget, but just doing it graphically, that you can change the carrier frequency. This is distance versus signal to noise ratio. You can change the loss component, so you can change the environment you're working in. This is an example of the interactive questions. So that's what they would look like. And there's a whole set of these in there. I'm not going to go through these now. However, I will point out one thing is that after I had this all written, there was a new object, a question object that was added in that makes it a lot easier to add those questions in than what I did. So you can just put your answer in, and now there's a built-in function to do that, which is very nice. Okay, to wrap it up, I felt that I was able to get more of an interactive engagement of the students using this approach. Just to give you an idea that some of the student comments I got back, they were addressing what aspects of the class were most helpful to your learning. One said the best part of the class was the interactive book, since the graphs and tables with changeable parameters allowed for very good understanding, since you could physically see what's happening. Having actual examples to reference in the electronic book during the homework was helpful. Sample problems in the book with automatic checking. Student to relate it to real world examples, you know, they don't use proper English sometimes when they write their comments, but one student said it was really neato to have real world examples. And that basically wraps up the presentation. So with that, I'll quit sharing my screen and answer any questions anyone may have. It says, how much work was preparing this book compared to what you did lectures before Mathematica? Well, that's kind of hard to say because I've been teaching this class since about 1982, so I had a whole set of notes that I worked from. Luckily or unluckily, the first semester of the pandemic, fall 2000, I was on sabbatical. So basically, I used my sabbatical to transfer my notes into this ebook. Yeah, in terms of preparing a complete OFDM system from one end to the other, there is that in my ebook. I didn't do the example, but I do that. It's I go through from the bits to the samples to using the FFTs and inverse DFTs in the receivers. So all that is in the ebook. And it can always be enhanced. The other thing, if anybody, you know, I'm willing to provide the notebook that the ebook is based on to any instructor. I don't want to give it to students, but yeah, it's there. A very simple case, obviously it's introduction. So I think I do two orthogonal carriers transmitting QPSK. Yeah, the code's in the notebook that the ebook is in. I really only want to give it to instructors, so you'd have to you know, send me some information about where you're teaching and I'll provide it. Next one is there support for building movies that show something happens? For instance, if you wanted to show how EM fields propagated. That's a Mathematica question. That's for Wolfram. The one thing I will point out is that somebody a few years ago wrote a calculus book using Mathematica, and they used the vector. They had it at the end of that book. They have vector calculus, which show the curl and divergence graphically using Mathematica interactive graphics that were very interesting. So if you want to see some of that, I'd check out that calculus book. I don't remember who wrote it, but I'm sure you can Google it and find out.
We're about out of time, but is there a good way for people to get a hold of you if they have further questions, send an email, things like that?
Yes, it's vsfrost@ku.edu. Frost@ku.edu also works. So just my last name I'm at the University of Kansas. That works.
Terrific. All right. Well, we'll go ahead and wrap things up. Thanks very much, Victor.
You're welcome. Thanks for everybody for listening.